So analysis of discrete time LTI system. So welcome to GATE class. So today we will discuss the Z transform. So basically the analysis of discrete time LTI system can be done using Z transform. Can be done using Z transform. So if you remember the Laplace transform we have used to do the continuous time LTI system analysis, same wise this discrete time Z for the counterpart of continuous time LTI system, that is discrete time LTI system, the analysis can be performed using the Z transform. So basically what is Z transform? So Z transform is a powerful mathematical tool to convert differential equations into algebraic equations. So it is very powerful. Okay, so it is a powerful mathematical tool to convert differential equation into algebraic equations. So what is the definition of Z transform? So the bilateral or you can say that it is two-sided. There is unilateral and there is bilateral. So right now I am discussing the bilateral. So the bilateral Z transform of a discrete time LTI system is defined as xz, and that discrete time LTI system xn is defined as xz, that is Z transform of xn, and it is equal to summation en is equal to minus infinity to plus infinity xn z raised to the power minus n. So I am again writing so that xn is our discrete time sequence, xn is our discrete time signal, and the Z transform is given as xz, and it is Z transform of xn, and it is, by the definition, is n is equal to minus infinity to n is equal to plus infinity xn z raised to the power minus n. So likewise we can define the Z transform for unilateral case also. So the unilateral, that is one-sided, the unilateral or one-sided Z transform of a discrete time signal xn is given as, let it is x1z, so it is equal to Z transform of xn, that is summation, it will go from n is equal to 0 to infinity. That's why I am saying it is unilateral, xn z raised to the power minus n. Okay, so basically if we are talking about the Z transform, then Z transform may exist for some signals for which discrete time Fourier transform does not exist. So it is very important to note that, the Z transform may exist may exist for some signals for which discrete time Fourier transform DTFT does not exist. Okay, so please understand that the Z transform may exist for some signals for which the discrete time Fourier transform does not exist. Now we have another thing is we have the concept of, let us discuss the concept of Z transform and also discuss the inverse Z transform. So let us discuss the concept of Z transform and how this concept of Z transform is related to your Fourier transform and all these things. So let us discuss the concept of Z transform. Concept of Z transform. So Z transform of a discrete time signal is defined as xz, and that is equals to summation n is equals to minus infinity to plus infinity xn z raised to the power minus n. So let this is equation number 1. Now if we take z is equals to r e raised to the power j omega, if we take z is equals to r is raised to the power j omega, so basically we have written this in the form of polar form. So it is just like a circle you assume, and r is nothing but the radius of the circle. So r is nothing but the radius of the circle. So this is the radius of the circle, and it is making an angle omega. So it is represented, because z is basically complex symbol. Z is a complex symbol. So we can represent this complex symbol in this polar form. So using this z is equals to r is to the power j omega in equation 1, what we will get, we obtain x r e raised to the power j omega is equals to summation n is equals to minus infinity to n is equals to plus infinity xn r e raised to the power j omega minus n. Just we have put the value of z, that is r is e raised to the power j omega, and so it will become n is equals to minus infinity to plus infinity xn r raised to the power minus n e raised to the power minus j omega n. Now we can write it as, if we analyze this expression carefully, then r e raised to the power j omega, if we analyze that is equals to xz, then we have z is equals to r e raised to the power j omega. That is nothing but the Fourier transform. of xn r raised to the power minus n. that is nothing but the Fourier transform of x n r raised to the power minus n. Okay, so that is discrete time Fourier transform. If you don't know discrete time Fourier transform, let me tell you what is discrete time Fourier transform. So if you have signal xn, then the discrete time Fourier transform of this discrete time Fourier transform of this xn is summation n is equals to minus infinity to n is equals to plus infinity xn e raised to the power minus j omega n. So here we have e raised to the power j minus j omega n. Here we have e raised to the power minus j omega n. So this whole term we can take as input. So this is nothing but the discrete time Fourier transform of xn. This is nothing but the discrete time Fourier transform of xn r raised to the power minus n. So this is equation number 2. Let this is equation number 2. Let this is equation number 2. So the above equation, so if we analyze carefully, so equation 2 represents the relation between the Fourier transform and Z transform. So xz, that is Z transform, when we have Z is equals to e raised to the power j omega, here r is equals to 1, what we will get? We will get discrete time Fourier transform of xn. Perfectly, we are getting discrete time Fourier transform of xn. So r is equals to 1 means we are considering the unit circle. We are considering the unit circle. So the circle has radius 1, so we are considering the unit circle. Because r is equals to 1. So r is equals to 1 means unit circle, because the radius is 1. So when you have when you have r is equals to 1, so the Z transform will converge to discrete time Fourier transform. The Z transform will converge to discrete time Fourier transform of xn. So this is very important point. Please understand that your Z transform will converges to Fourier transform, discrete time Fourier transform, when you have unit circle, at unit circle. Now let us see the inverse. Z transform. So what is inverse Z transform? So let us start with the relation that xr is e raised to the power j omega is discrete time Fourier transform of xn r raised to the power minus n. Now xn r raised to the power minus n is nothing but the DTFT inverse of x r e raised to the power j omega. Okay, now what is xn? So xn is nothing but r raised to the power n multiplied by DTFT inverse of x r e raised to the power j omega. So what we will get finally, that r raised to the power n is basically, if we just see the relation, then if we concentrate on this as a continuous time series, then it is x e raised to the r e raised to the power j omega in continuous, and e raised to the power j omega n into day omega. So it is nothing but the 1 divided by 2 pi, it is written, and 1 divided by 2 pi x r e raised to the power j omega r e raised to the power j omega n into d omega. So this is equation number 3. This is equation number 3. Now let us substitute r e raised to the power j omega is equals to z in equation 3. What we will get? We will get, if we differentiate, we will get dz is equals to jr e raised to the power j omega d omega is equals to z. Okay, so what we will get, okay, jz d omega. Okay, now so what is d omega? So d omega is nothing but 1 divided by j, z inverse of dz. Now we can substitute this d omega value in equation 3. So d omega, so substituting d omega in equation 3, we get xn, that is xn, that is discrete time signal. In discrete time domain, xn is related to xz with the following relation. It is 1 divided by 2 pi j integration xz z raised to the power n minus 1 dz. So please understand, this is basically the inverse Laplace transform. This is basically the inverse Laplace transform. So I am summarizing. So the derivation, they are in GATE they are not asking about the derivation, but you have to remember the final result. So the final result is for xz, for calculation of xz, the formula is xz is equals to summation n is equals to minus infinity to plus infinity xn z raised to the power minus n. And if you want to find out the discrete that inverse z transform, then it is equals to 1 divided by 2 pi j integration of xz z raised to the power n minus 1 dz. So okay, so this is your z transform, this is your z transform, and this is your inverse z transform. This is your inverse z transform. So please understand that this is your z transform and this is your inverse z transform. In this way you can find out the inverse z transform. So there are some properties of z transform. There are some properties of z transform. So z transform has following properties. Z transform has following properties. So what are the properties of Z transform? So first property is linearity property. First property is linearity property. First property is linearity property. So what is that property? So if xn has Z transform xz and yn has Z transform yz, then the linearity property says that axn plus byn, the Z transform of this signal is nothing but axz plus byz. So if xn has Z transform xz, if yn has Z transform yz, then axn plus byn has Z transform axz plus byz. So this is simply the linearity property we have discussed in case of continuous time signal also. Then we have second property. That property is called time shifting property. That property is called time shifting property. So what is that property? What is the time shifting property? So according to this property, if xn has Z transform xz, then time shifting property states that states that exn minus 1, because we are going to shift the time, n to n minus m. So that z transform is, we are getting the z transform that is equal to z raised to the power minus m into xz, that is equal to z raised to the power minus m into xz. So this is called the time shifting property. Another property is multiplication by exponential sequence property. So another property is multiplication by exponential sequence property. Exponential sequence property. Multiplication by exponential sequence property. So let us discuss this property. So property says that if xn has z transform, xz, then what we will get after multiplication? Then multiplication by an exponential sequence property states that then multiplication by an exponential sequence property states that a raised to the power n xn, if we find out the z transform, then it is equal to xz by a, So this property is called the multiplication by exponential sequence property. So if you have xn, that z transform of xn is xz, and then if you multiply with a raised to the power n into xn, what will we get? The z transform will be xz by a. So this is called the multiplication. By exponential sequence property. Then we have time reversal property. And what property says that if xn has z transform xz, then what is that property? Time reversal property. Then the time reversal property says that the time reversal property states that if we take x minus n, then the z transform is equal to x1 by z. Next property is differentiation is in z domain or multiplication by n property. Next property is called differentiation in z domain or multiplication by n property. This property is called differentiation in z domain or multiplication by n property. So likewise in your continuous time, if you have xt, the Laplace transform is xs, if you remember, then minus t into xt, you will get the Laplace transform minus dxs divided by ds. Likewise here in our z transform, if xn has z transform, if xn has Z transform xz, xn has Z transform xz, then multiplication by n, then multiplication by n, or differentiation in Z domain property says that in Z domain property states that n raised to the power k xn, n raised to the power k xn, the Z transform is equals to minus 1 raised to the power k zk d raised to the power k xz divided by dz raised to the power k. I am again writing this property. So n raised to the power k xn, the z transform is nothing equals to is nothing but it is equals to minus 1 raised to the power k zk d raised to the power k xz divided by z raised to the power k. So here we are we have taken that k derivative of xz with respect to z. So d raised to the power k xz divided by z at dzk is basically the k derivative of xz with respect to z. And next property is very important property that we are dealing with in continuous in discrete time case. It is called the convolution property. It is called the convolution property. So what is that property? If xn has Z transform xz and yn has Z transform yz, then the convolution property states that convolution property states that exn convolution with yn has Z transform equals to xz multiplied by yz, has Z transform xz multiplied by yz. So again we are able to see that that convolution in time domain, that is discrete time domain, is equals to multiplication in Z domain. Here we can see that the convolution in discrete time domain, that is this is discrete time domain, convolution in discrete time domain is equals to multiplication in Z domain is equals to multiplication in Z domain. Next property is correlation property. So what is that property? So according to this property, if xn has Z transform xz and yn has Z transform equals to yz, then correlation property states that exn correlation with yn is equals to, if we take the Z transform of that, then it is equals to xz, multiplied by yz inverse, then it is equals to xz multiplied by yz inverse. So this is called the correlation property. Next property is initial value theorem. Next property is initial value theorem. Next property is initial value theorem. So what is that initial value theorem? So according to this property, for a causal signal xn, so for a causal signal xn, the initial value theorem states that ex0, that is the initial value at n is equals to 0. This is the initial value, that is equals to limit z tends to infinity xz. So this is used to find out the initial value of signal without taking the inverse Z transform. So this property, so if you just see that, if you analyze this expression, then you can find out that if you know the xz, if xz is given, so what is that property? If xz is given, then we can find out the initial value. We can find out the initial value used by using this initial value theorem. We can find out the initial value of xn by using the initial value theorem. So what is that property? So this is used to find out, this is used to find out the initial value. This is used to find out the initial value of the signal without taking inverse Z transform, without taking the inverse Z transform, without taking the inverse Z transform. Now find out, now another is final value theorem. So for a causal signal xn, xn, the final value theorem states that x infinity, that is the final value at n is equals to infinity, that x infinity, the final value is nothing but limit z tends to 1, z minus 1 into xz. This property is called the final value theorem. So this is used to find out the final value of the signal without taking inverse Z transform. Again, the important point is that without taking the inverse Z transform, we can find out the final value. So this theorem states that this theorem is used to find out the final value, the final value of the signal without taking inverse Z transform, without taking the inverse Z transform, So these are some properties of the Z transform. Now let us discuss very important point, and that important point is basically the reason of convergence. Reason of convergence. This important point is the reason of convergence of Z transform. So what is reason of convergence? the range of variation of z, the range of variation of z for which Z transform converges, is called the region of convergence, So let us discuss one problem, and by using that problem we can analyze the region of convergence. So the example is, let us take xn is equals to del n. Let us take xn is equals to del n. Now we can find out the z transform of this signal. So what is z transform? It is xz is equals to summation n is equals to minus infinity to plus infinity exn z raised to the power minus n, and that is equals to summation n is equals to minus infinity to plus infinity. Using the value of xn in this, it is del n z raised to the power minus n, and it is equals to n is equals to minus infinity to plus infinity del n z raised to the power minus 0, because if you remember the property, sampling property, if we multiply xn with del n minus n naught, it is equals to xn naught del n minus n naught. So like this property we can use here. So here instead of xn we have this z raised to the power minus n. So we have the delay is n naught is 0, n naught is 0. So here we can find that we have z raised to the power minus 0 multiplied by del n. So it is nothing but we can go from n is equals to minus infinity to plus infinity del n. Now we are going to sum the del n, that is unit sample, from minus infinity to plus infinity, and we know that at n is equal to 0 its value is 1, and all other values it is equal to 0, because if we see the graph of del n, we can find out at n is equal to 0 the value is 1, and all other values it is 0, so the summation of this is 1. Now can we see the region of convergence in which the series will converge? Yes, of course, the region of convergence is entire z plane. So what is the ROC? So the ROC is entire z plane, So if you remember, just recall the continuous time case, the del t has Laplace transform 1, and the region of convergence is entire S plane, and the region of convergence is entire S plane. Let us discuss another problem, then we will better analyze the region of convergence. So let us take xn is equals to a raised to the power n into un, and this signal un is all of us know that un is equals to 1 for n greater than or equal to 0. It is 0 for n less than 0. Now can we find out the z transform? Of course, the summation it will go from n is equals to minus infinity to plus infinity xn z raised to the power minus n, and it is equals to summation n is equals to minus infinity to plus infinity a raised to the power n un, then z raised to the power minus n, and it will go from n is equals to 0 to infinity a raised to the power n into 1 into z raised to the power minus n, and it is equals to n is equals to 0 to infinity a z inverse raised to the power n. Now let us discuss this series expansion. So xz is summation n is equals to 0 to infinity a z inverse raised to the power n. Now in which case the series will converge? We have two cases. So case 1, that magnitude of this quantity is less than 1, and case 2, the magnitude of this quantity is greater than 1. So in which case the series will converge and in which case the series will diverge. So if we see carefully, then we will find out that if we have a modulus of A z inverse less than 1, then the series will converge. The series will converge. And in this case, the series will diverge. The series will diverge. So this is the case of divergence. This is the case of convergence. So basically we are considering this case. So we will consider this case, and the Z transform by considering this case is Az inverse raised to the power 0 plus Az inverse raised to the power 1 plus dot dot dot, it is infinite Gp. So it is 1 divided by 1 minus Az inverse. And what is the ROC? What is the ROC? So the ROC is if we write in this form A divided by Z less than 1, then mod A less than mod Z. So let us discuss this again. So what we got here, we got that xz is nothing but 1 divided by 1 minus Az inverse, and the ROC is mod Z greater than mod A. Now we can see that what is that meaning, modulus of Z greater than mod A, what is the meaning? So we have a circle of radius A, and the ROC is outside this, and the ROC is outside this. So this is the Z plane, this is the Z plane, this is real part of Z, this is imaginary part of Z, this is the Z plane. So it is mod Z greater than A means it is outside the circle. It is outside the circle. So the reason of convergence is modulus of Z should be greater than modulus of A. So this is the reason of convergence for the this Z transform. Let us do Laplace this Z transform of some basic sequences. So let us do that Z transform for this sequence, that is xn is given as, so this is the example, so xn is given as 5 3 minus 2 0 4 3. So this is the sequence, and there is an arrow at that point at minus 2. So find out the Z transform. So find out the Z transform and reason of convergence. Find out the Z transform and reason of convergence. So xn is given as 5 3 minus 2 0 4 3. So arrow is given at minus 2. It means it is for n is equals to 0 point. So if we draw the graph of xn, if we draw the graph of xn with n, then at n is equals to 0, the value is minus 2. And at n is equals to 1, the value is 0. At n is equals to 2, the value is 4. At n is equals to 2, so it is n is equals to 1, it is n is equals to 2, it is n is equals to 3. So at n is equals to 3, the value is 3. Now at n is equals to minus 1, the value is again 3. At n is equals to minus 2, the value is 5. The value is 5. So this is our xn. This is our xn with n. Now we can find out the Z transform. We can find out the Z transform xz, and it is summation n is equals to minus infinity to plus infinity xn z raised to the power minus n. Now xn can be written in the form of unit samples. So how to written in the form of unit samples? So please check, it is minus 2 del n minus 0 plus 0 multiplied by del n minus 1 plus 4 multiplied by del n minus 2 plus 3 multiplied by del n minus 3 plus 3 multiplied by del n plus 1 plus 5 del n plus 2. So xn is written as minus 2 del n plus 4 del n minus 2 plus 3 del n minus 3 plus 3 del n plus 1 plus 5 del n plus 2. So this is a minus 2 del n. Then we have 4 del n minus 2. Then we have 3 del n minus 3. Then we have 3 del n minus plus del n plus 1 plus 5 del n plus 2. So this is our xn. So the z transform is equals to, please find out the z transform is equals to, the z transform is nothing but 2z raised to the power minus 0. Please understand that plus into plus, we just applying the sampling property here. So it is 2z raised to the power minus 0 plus 0 into z raised to the power minus 1 plus 4 into z raised to the power minus 2 plus 3 into z raised to the power minus 3 plus 3 into z raised to the power 1 plus 5 into z raised to the power 2. So this is our z transform. So this is our z transform of xn. So it is, please again I am saying that it is minus 2z raised to the power minus 0. Here n is equals to 0. Then we have 0 multiplied by z raised to the power minus 1, because here n is equals to 1. Then we have 4 into z raised to the power minus 2. Then 3 into z raised to the power minus 3. And if we go for negative n, then n is equals to 1 minus 1. It is 3z inverse plus 5z raised to the power minus plus 5z raised to the power 2. So xz is written as minus 2, z raised to the power minus 0 is nothing but it is equals to 1. So minus 2 plus 4z raised to the power minus 2 plus 3z raised to the power 1 plus 5z raised to the power 2 plus 3z raised to the power minus 3. So it is minus 2 plus 4z raised to the power minus 2 plus 3z raised to the power minus 3 plus 3z plus 5z square. So this is the z transform. This is the z transform. Now if we talk the ROC of this z transform, then the ROC is, we can say that the ROC is entire z plane. Please check this. The ROC is entire z plane except. So what are the points that we have to exclude from the region of convergence? So if we analyze this, then at z is equals to 0, if we, at z is equals to 0, it will tends to infinity. At z is equals to 0, it will tends to infinity. And if we see that at this term, it will tends to infinity at when z tends to infinity. So except z is equals to 0 and z is equals to infinity, entire s plane is our entire z plane is the region of convergence. So region of convergence for this question is, it is entire z plane except z is equals to 0 and z is equals to infinity. It is the entire z plane except z is equals to 0 and z is equals to infinity. So let us discuss, let us solve this problem. So let us solve this problem. The xn is given as 1 by 2 raised to the power n un plus 1 by 3 raised to the power n un. So xn is given as 1 by 2 raised to the power n un plus 1 by 3 raised to the power n un. So let us solve this problem. So xz is given as summation n is equals to minus infinity to n is equals to plus infinity xn z raised to the power minus n and it is equals to n is equals to minus infinity to plus infinity 1 by 2 raised to the power n u n plus 1 by 3 raised to the power n u n z raised to the power minus n, and it is equals to summation n is equals to minus infinity to plus infinity 1 raised to the power n u n z raised to the power minus n plus summation n is equals to minus infinity to plus infinity 1 by 3 raised to the power n u n z raised to the power minus n. So it can be written as, if we consider the definition of un, then it is equals to from n is equals to 0 to n is equals to infinity, its value is 1. So what we will get? We will get 1 by 2 raised to the power n z minus n plus n is equals to 0 to infinity 1 by 3 raised to the power n z raised to the power minus n. So it can written as n is equals to 0 to infinity 1 by 2 z raised to the power minus n, the power is n, plus summation n is equals to 0 to infinity 1 by 3 z raised to the power minus n raised to the power n. So it is basically, if we put n is equals to 0, then it is equals to 1 by 2 z inverse raised to the power 0 plus 1 by 2 z inverse raised to the power 1 plus 1 by 2 z inverse raised to the power 2 plus dot 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 plus 1 by 3 z raised to the power minus 1 raised to the power 0 plus 1 by 3 z raised to the power minus 1 raised to the power 1 plus dot dot dot. So this is xz. Now we can see that the convergence of this series, for the convergence of this series, if we see the convergence, if xz will converge, then we have to satisfy the following conditions. So the first case, summation n is equals to 0 to n is equals to infinity 1 by 2 z 1 dash raised to the power minus n, in this should be less than 1. So what we will get? We will get 1 by modulus of 1 by 2 less than mod z, and mod z greater than 1 by 2. So this is the first ROC. And second one is, we have summation n is equals to 0 to infinity 1 by 3 z inverse raised to the power n. So it should be 1 by 3 z inverse, it should be less than 1. So it should be mod z should be greater than 1 by 3. So final result is 1 divided by 1 minus 1 divided by z inverse plus 1 divided by 1 minus 1 divided by 3 z inverse. So this is the final xz. And what is the common ROC? So first is mod z greater than 1 by 3. 1 by 3 is 0.333. So it is 1 by 3, it is minus 1 by 3, then it is minus 1 by 3, it is 1 by 3. Second is mod z greater than 1 by 2. So it should be here at some point. It is 0.5 greater than 1 by 3. So it is 1 by 2. It is minus 1 by 2. It is minus 1 by 2, it is plus 1 by 2. So now we can say that the ROC is mod z greater than 1 by 3, and it is also mod z greater than 1 by 2. So if we combine ROC, so the first ROC is mod z greater than 1 by 3. So this is exterior for this circle. Second one is that mod z greater than 1 by 2. So this is exterior for that circle. Now the common ROC, we plot the common ROC, we will find out the common ROC is basically we have 1 by 2 minus 1 by 2. This is minus 1 by 3, minus 1 by 2, this is minus 1 by 2. So the common ROC is, this is the common ROC, this is the common ROC. So the common ROC is mod z greater than 1 by 2. So the ROC is mod z greater than 1 by 2. Now this ROC includes the unit circle. So here we have unit circle, here we have unit circle. So this is the unit circle. Since the ROC includes the unit circle, so system is stable. Since the ROC includes the unit circle, the system is stable. Let us do another problem. So the problem is a finite sequence xn. A finite sequence xn is defined as xn is equals to, it is not equals to 0 and it is equals to 0. When it is not equals to 0, then n1 is less than or equal to small n less than or equal to n2. So between n1 and n2 it is not equals to 0 and it is 0 to otherwise for all other values of n. So where n1 and n2 are finite. So let us show that ROC of xz is the entire z plane, so that the ROC of xz is the entire z plane except or possibly z is equals to 0 or z is equals to infinite. So these two, except these two values, we can find out the z transform. So xz is written as summation of n is equals to minus infinity to plus infinity xn z raised to the power minus n. And since it is between the range n1 and n2, it is only past there. So it is between n1 and n2 we have xn, all other values it is 0. So xz is summation n is equals to n1 capital N1 to n is equals to capital N2 xn z raised to the power minus n. Now we can analyze this expression. So for z not equals to 0 or infinity, each term, if we see that for z not equals to 0 and infinity, each term in equation 1 with finite each will be finite. Each term in 1 will be finite, and thus xz will converge, and and if the condition is if n1 is less than 0 or n2 is greater than 0, then equation 1 includes terms with both positive powers of z, and negative powers of z. So for example, if we are taking n1 is equals to -3 and n2 is equals to 2, then xz is nothing but summation n is equals to -3 to n is equals to 2. It is x n z raised to the power minus n, and it is equals to better to write in next slide. So xz is nothing but it is equals to x0 z raised to the power -0 plus x1 z raised to the power -1 plus x2 z raised to the power -2 plus x minus 1 z raised to the power 1 plus x minus 2 z raised to the power 2 plus x minus 3 z raised to the power -3, and so -3 z raised to the power +3, and so okay. So this is for when n1 is equals to -2 and -3 and n2 is equals to 2. So both negative and positive powers of z is there when we take n1 less than 0 and when we take n2 greater than 0. So both positive and negative powers of z present. So let us take that as we have both positive and negative powers of z. So when z tends to 0, when z tends to 0, what we are getting, the terms with negative powers of z. So the terms with negative powers of z, the terms because we have negative powers of z, so when z tends to infinity, the xz will become unbounded. The xz will become unbounded, and when we have z tends to infinity, then due to this positive powers of z, the xz will become unbounded. So it will become, the xz will become unbounded. So hence with positive powers of z, it will become unbounded. Hence the ROC is entire z plane. So the ROC is entire z plane except the ROC is entire z plane except z is equals to 0 and z is equals to infinity when n1 is less than 0 and n2 is greater than 0 and n2 is greater than 0. So another case is if n1 greater than or equal to 0, so equation 1 contains only negative powers of z. Okay, when n1 is greater than or equal to 0, so in this case both positive and only negative powers of z exist because n2 is also greater than 0. So so what will happen that the ROC includes, the ROC means is entire z plane. ROC is entire z plane and it also includes the infinity. So basically if we have only negative powers of z, then the ROC is entire z plane and also it includes z is equals to infinity, but for z is equals to 0, the xz will become unbounded because that 1 divided by z, when z tends to equals to 0, it will become unbounded. Now another case is that if n2 is less than or equal to 0. Now if n2 is less than or equal to 0, then what will happen that the ROC will include z is equals to 0, no problem. The ROC will include z is equals to 0, but for z is equals to infinity, the xz will tends to unbounded. The xz will tends to unbounded. The xz will tends to unbounded because when we have n2 less than or equal to 0 and n1 is already negative, so we will get only positive powers of z. So as we are getting only positive powers of z, so what will happen that z is equals to 0, no problem, the xz will converge. But when we put z is equals to infinity, then it will not converge. So basically we will get unbounded result. So all these things are there. So it depends on the value of n1 and n2 whether z is equals to 0 is included in ROC or not included, whether z is equals to infinite is included in the ROC or not included. But the summary of this is that if xn is a finite sequence, then the ROC is the entire z plane except z is equals to 0 or z is equals to infinity.